Hi. Today we are going to discuss about the viscosity third part, and there mainly we discuss about terminal velocity, Stokes law, then terminal velocity and related questions. Okay. First of all, we'll consider about the motion of a solid or hollow sphere. It could be solid or hollow. This is falling or moving upwards. First, I'll consider falling downwards. Then, normally what happens is, we keep the sphere, we'll say solid sphere, like this. Due to the weight, it goes in. So, these things I'll explain after this. First, we'll discuss about Stokes law. Stokes law. When it is moving inside, there should be a friction, liquid friction. That friction is called viscous force. That is F against the motion. This is the direction of the motion. Then we will consider its other things. That velocity is V. Eta is the viscosity of the medium. Medium means the liquid, it falls. It could be even in air. Air is also having viscous force. So air is concerned, water droplet is falling. Here in water or any other liquid, solid sphere or hollow sphere is falling down. It can be moving up also, but first we'll consider downwards. And its radius, the sphere radius is A. So then, this frictional force or viscous force depends on a radius of the sphere, liquid coefficient of viscosity, velocity. So it depends on. So anyhow, we can prove this equation. F is equal to K A eta V. This K value is 8.5. So then F is equal to 8.5 A eta V. Then start right, Stokes law. When a sphere, whether it is hollow or solid, falls in a viscous medium, that means in a liquid or in air, so then it is, this K is 6.5, not 8.5, 6.5 A eta V. Then in air or liquid, then there is a, note down, viscous force against the motion. Against the motion. This frictional force depends on radius of the sphere, velocity of the sphere, and coefficient of viscosity of the medium, that is liquid or air according to the situation, or any gas. Then we can prove the equation F is K A eta V. This K is 6.5. Once I said 8.5, that is 6.5. So then, therefore, the equation can be written as F equals 6 pi A eta V. This is called Stokes law. According to Stokes law, the frictional force depends on these things. But even these equations is written, sometimes they give the marks. Then write below that Stokes law definition. When a solid or hollow sphere moving vertically up or down in a viscous medium, the viscous force exerted on the sphere depends on its radius and the velocity of the sphere and the coefficient of viscosity of the medium it travels. That method also they are giving this. Sometimes directly they say this way also they will accept. Then write when a solid or hollow sphere moving vertically down or up in a viscous medium, the viscous force exerted on the sphere is directly proportional to its radius within brackets you write external. The reason is when it is a hollow one, it is external one, not the internal radius. External, close the bracket, and its velocity and coefficient of viscosity of the viscous medium. Or you can say traveling medium. Traveling medium. That's the three ways. The last one is better. Even they accept when you write the equation. Remember this is 6 pi A eta B. Right. Now I'll explain how we get this also we can prove it. The proof is not asked under this section directly because it's under first unit. But I will do it. Anyhow, this is how you have to consider first. When it is situations, we can consider like this. This is the solid sphere A. Directly, this is liquid. Normal. Even in the gas, it's okay. Gas, air, anything. Hello. Hello. Yes, I know that I have paid that one. I'm on a lecture at the moment. I will do it today. I know that. I'm updated with that. Hello. I'll do it today. I know it. Then we have to consider second situation. This is air. Then the other one, this is solid. When it is normally solid in liquid is a normal situation. Solid, this is liquid, it is normal situation. But even in air or gas, it can be. The second situation, liquid one, just like water droplet, liquid, water, or any liquid. This falls in air or gas or air or gas. This is the two situation. Even that viscous force we can use for both situation. F equals 6 pi A eta V. So F is equal to 6 pi A eta V. Got it? Then we can apply this. Even it is a hollow sphere, then this is A1, this is A2. In this case, we are getting, when it is hollow, external one. A2 is equal to A. Then F equals 6 pi A2 eta V. It is not, A is unequal to which one? A is unequal to A1, internal radius. Note down all those. All situations you have to understand properly. All these situations. This is the solid one falling in liquid, gas or air. Here, this is a solid one. In liquid is a normal question type. Liquid, just like a water droplet, falling just like falling one raindrop. So then air or gas, normally raindrop is concerned air. Another situation I'll take. All are falling down, these things. All these falling down. Vertically falling down means vertically down. Next situation. In the next situation, I can consider something which is moving upwards. Situation is, we'll say, solid sphere. Radius is A, moving upwards, right, with the velocity of V. Now against the motion, you get the viscous force. So eta is this. But situation, same. So equation is the same. F equals 6 pi A eta V, even. Situation, when I say solid, you might think that how it happens. Always you feel that it's a metal or, we'll say this is liquid, water. This is a solid sphere having less density than water. Could be rubber ball, maybe it's hollow also, but here I said solid, rubber density is less than water density, frigiform, like that. Then it's going up. And very famous situation is air bubble. Air bubble is moving upwards. Same equation. So then, now air density of air is less than water. It's obvious. So this situation, this sphere is moving up. Even that we can apply Stokes law, F equals 6 pi A eta V. even this, if you consider this solid one, a hollow sphere, then A1 is this, A2 is this, moving upwards V, and again A2 is to be considered external. F is equal to 6, 5, A2 eta V. I'm using A1, A2 because to understand properly the external radius. Not down. Now we'll consider how to get this equation using dimensional analysis. That's first unit, but anyhow I'll do it. Here, situation is this. Sphere falling down with V, frictional force is F, radius is, but you know it can be applied for anything, but we'll prove for solid one. Eta, and F is, now F depends on A, eta, and V. V is the velocity. I explained it earlier, therefore I directly wrote it. Now we write F equals Ka x eta y V z. K is a dimensionless constant. After that, x, y, z are powers we have to find. Now, dimensions of F. M, L, T minus 2 is supposed to. Dimensions of A. L. Dimensions of eta. ML minus 1, T minus 1. And dimensions of velocity. LT minus 1. So then we came up to dimensions. After that, you have to substitute these values there. When you come to this one, then we have to substitute the values. When you are substituting the values, directly we will substitute this one. M, L, T minus 2 is equal to K, L to the power X. There is no need to write brackets. Next one, eta, ML minus 1, T minus 1, Y, and LT minus 1, LT minus 1 to the power Z. Now this is M, L, T minus 2, K, L, X, M, Y, L minus Y, multiplication of the powers. 1 into Y minus 1 into Y minus 1 into Y. T minus Y, L, Z, T minus Z. Then take the same ones together. Same base. Lx, L minus Y, Lz, My, then T. T is concerned minus Y minus Z. T minus Z. Then we can consider ML, t minus 2. Right up to this, I can do it there. So then m L t minus 2, then you get k L x minus y plus z L x L x minus y plus z. Then m is concerned on the y. Then we have to consider t. T is considered minus y minus z. By equating the powers of each dimension, then you get, first we'll consider m. Then directly from this we can write power is 1 y. 1 is equal to y. Then we got a value for y. Then we'll consider t. T is concerned, then you get minus 2 is equal to minus y minus z. Minus 2 is equal to minus 1 minus z. This. Then you get this z is taken to this direction to the left. Z is equal to minus 1 plus 2. So z is also equal to 1. Then we want to find the other one, L. Now you consider L here. Then you get 1 is equal to x minus y plus z. Then 1 is equal to x unknown, y is minus 1, y minus y is 1 plus z. Z is equal to 1. Then minus 1 cancels off, x is equal to 1. Then we can find like that. Now substituting this in equation 1. Then you are getting substituting in equation number 1. Then after that, we are getting f equals a k ax eta y and vz. Vz. So f is equal to k a to the power 1, eta to the power 1, v to the power 1. All are 1. Then that means f is equal to k a eta v. But we are given k is equal to 6 phi. Therefore, f is equal to 6 phi a eta v. Quickly note down. Right, I think that is enough. Now we'll consider about the applications. Applications are very important, but this equation directly we don't use most of the equations, most of the questions, because it's easy. Anyhow, I'll give you one example. A radius of a steel ball is 4 millimeters and it's falling in a in certain oil. Certain oil. The viscosity, coefficient of viscosity of the oil is 1.6 into 10 to the power minus 3 then find the viscous force exerted on the sphere when its velocity is number 1 5 ms minus 1. Number 2, when it is 12 ms minus 1. Number 3, when the object is at rest. I want to change one thing. We'll change the viscosity value to 2.5. Not the given one, 2.5, cut and write, 2.5 without 10 to the power minus 3. We can have that is castor oil. This is coconut oil. I change it for easy calculation. Then F is equal to 6.5 A eta V. A is 4 millimeters. That means 4 into 10 to the power minus 3 meters. Now eta is given as 2.5 NSM minus 2. We can use that also if you want. Or other kgms minus 1. This minus 1 also can be used. Then V is first one. V is 5 ms minus 1. Then correct substitution means F is equal to 6. You know pi is 22 by 7, no 3.14. Normally whatever they give you use. A is 4 into 10 to the power minus 3. Then 2.5 into 5. There is no need to you write units here because we have already written there. There you are right. After that, you have to simplify this. After simplification, you get the value in newtons. Normally, since it is coming in newtons needed, I am using this NSM minus 2. Then automatically, I'll show you what is happening. If you want, get the value. So if I consider 6.5, A is in meters. Eta is nsm minus 2 and velocity is ms minus 1. So then here what you get is then m squared, m minus 2 cancel off. Then s minus 1, s cancel off. Then answer comes in Newton. Right up to that, then simplification can be done later. Now we'll come to normal situation. So this type of questions will rarely give because you can find it find the answer very easily. Second question you substitute 12 instead of 5 when it is s, that is 0. Third one directly v is 0, therefore f is 0. There is no need to substitute. Since v is 0, f is 0. So that means when it is not moving, nothing would happen. Now state another thing. This Stokes law is correct only there is a steady motion, steady flow. Then right? The Stokes law is correct when the motion is steady. Motion is steady. When a sphere is falling or moving upwards with a very high velocity, then it is not a steady motion. Better say steady motion. It is not steady motion. Then Stokes law is not applicable, or it is not true. For MCQs, A, B, C, three options are given, which one is correct or which ones are correct. Then remember, steady motion is there. Steady motion is normally very high velocity is there. This sphere motion is whether it's going up or down, it's not steady. Then you can't apply. That is there. That's a very important part for MCQs. Now I'll explain how we apply further for this. Some situations are there. I'm going to prove another equation, but it is not standard equation. Therefore, you can't use it at once. We'll see what it is. There are two situations. This is a sphere falling down in a liquid. But I'll draw the situations like this. First, it is just kept. Then, due to its weight, it should go in. So it may go like that, and finally it may be like that. Or another situation, but when it goes down into the liquid, additional force is also there. What is the additional force there? That is upthrust. So upthrust acts on this part of here. Upthrust. Upthrust. Here also for whole thing upthrust. Then upthrust. That is U, like that. Whole thing is there, I put it as or label as U. But it's moving down. Now it's moving down due to weight. But it reduces because its resultant force reduces because of the upthrust. We'll consider now it is in the liquid and moving with the velocity of V downwards. Then what are the forces acting on that? Sphere mg, then upthrust upwards, U, and it's acting at the same point. It's under hydrostatics. Center of buoyancy is the place where the upthrust acts on. But it is completely in the liquid, then mg is also acting like that. Normally, center of buoyancy means you have to consider the same identical liquid sphere. And its center of gravity is the center of buoyancy. So then solid one is concerned, it's a solid one. Then mg is at the center. Mg is at the center means center of gravity of the sphere is there. If you consider liquid sphere, that is also concerned, then it is at the center. So then both are acting at the center. Then the other one is the viscous force. Since it is moving down, it is against the motion. Now we'll consider radius is A. And eta is the coefficient of viscosity. Then I will consider what's happening here. Now look, when you consider this situation, I explain how it comes. Then now there is mg downwards, u upwards, f upwards. Then there is a resultant force downwards. There is a resultant force downwards. Resultant force downwards is equal to mg minus u minus f. In other words, mg minus u plus f within brackets. Now consider what's happening. Listen properly. Listen to me properly. Now resultant force is downwards. Therefore, there is an acceleration downwards. So therefore, velocity velocity of the sphere increases since it is an acceleration. According to Stokes law, F is equal to 6 pi a eta v. So for this one, eta is a constant. This is a constant. A is a constant. This is constant. So F is directly proportional to V. Therefore, V increases. What happened? Now V increases. Therefore, F increases. Upthrust is a constant because it's a upthrust is equal to weight of the liquid displaced by the sphere. Weight of the liquid, not mass, it is weight of the liquid displaced by the sphere. So U is also constant. So here I mark U as constant, mg is constant. R depends on F. Now velocity increases, F increases. Then now this situation, U plus F is at the present situation, greater than U plus F previous. Because previous now F increases, no? So it increases and there is a particular situation, U plus F is equal to mg. Even F increases, there is a resultant force downwards. But there is a situation, then velocity increases, again F increases. Then U plus F increases in the course of time. Then there is a situation, U plus F is equal to mg. Then U plus F is equal to mg means R becomes mg minus U plus F. That means this becomes 0. No resultant force downwards. Therefore, according to F equals ma, acceleration becomes 0. I'll give a note, but you just draw it and note down. So I wrote from this side, then I came to this side. Don't draw. Always I am writing, I am starting from the right hand side of the board because it does not cover from my body. Normally everybody is writing from left to right, no? Here it is different way I am writing. Always remember, after that, this is the part. After this, third part. Or if I draw the arrow here, if you want to go up like that. Quickly note down. After that, I'll give the note. Right, now I'm giving the note. Start like this. When a sphere is kept on the free surface of a liquid, due to the weight of the sphere, it goes into the liquid. Then there is a upthrust acts on it. When you come to the third diagram here, 1, 2, 3, third diagram, the sphere is almost inside the liquid. Then the complete upthrust is there. Then the complete upthrust is acting there on the sphere. Right property. Even the sphere is inside liquid further, upthrust is the same. It's a constant value. Normally, upthrust is equal to weight of the liquid. Weight of the liquid displaced by the object. After that, we can consider fourth diagram. Since there is a resultant force vertically downwards, it gets an acceleration and the sphere is getting a velocity. When there is a velocity, according to Stokes Law, viscous force is there and so there is a viscous force. Now we can consider the resultant on the fourth diagram. The resultant on the fourth diagram is concerned. It is equal to, note down, R equals mg minus u minus f. And then again write this. Since there is an acceleration, since there is a resultant force downwards, according to the equation F equals ma, there should be an acceleration vertically downwards. Since there is an acceleration, velocity of the sphere increases. In this situation, according to Stokes law, 6 phi is a constant. The given sphere radius is constant. If the temperature does not change, we assume like that, the velocity of the sphere, that is constant. In other words, 6 phi is a constant, radius is a constant, when the temperature is constant, eta is a constant. But V increases. Then F is directly proportional to V. F is directly proportional to V, then we get the velocity. Now I said there is an acceleration, velocity increases, then viscous force increases. Then right? Since 6, phi, A and eta are constant values, viscous force is directly proportional to V or velocity. Velocity. Now, if we consider U plus F value, F increases, therefore U plus F. Then right? Now U plus F value increases. U plus F value increases. Then the resultant force, which is mg minus U plus F, like this one, reduces. Resultant force reduces. But there is a resultant force. But that resultant force now acting is still there and it is less. Then right? This resultant force is less than earlier. Therefore, acceleration is less. Acceleration is less. Now there is an acceleration still, but that value is less than earlier. Less than earlier. But velocity still increases. But velocity still increases. Again, F value of viscous force increases. That means U plus F increases. The resultant force reduces further. According to this resultant force, according to this, decreases. Sometimes in books they use the word diminishes, decreases further and further, and there is a situation U plus F is equal to mg. Note down this one. U plus equal to mg. Then resultant force is 0. After that you write this one. Now, since there is no resultant force, acceleration becomes 0. After this instant, this instant, that means either U plus F is equal to mg or acceleration is 0. Instant, no increase, right? Not down. No increase in the velocity of the sphere. Now, the sphere has come to the maximum velocity. After that, no increase in the velocity. This maximum velocity is called terminal velocity. This is called terminal velocity. So then after reaching the terminal velocity, no increase in the velocity further in the sphere. Then right, there is no further increase in the velocity of the sphere. When we consider key points, number one, first you write just like a heading. When the sphere falls down, viscous force increases. Number one, viscous force increases. Number two, acceleration of the sphere decreases and comes to zero. Third one, when acceleration becomes zero, that situation is called terminal velocity situation. Within brackets you write, normally we say that the sphere has attained the terminal velocity. Attained the terminal velocity. Now we can understand what's happening when the sphere is falling down. If I consider a graph, VT graph, velocity time graph, right? Now consider velocity time graph for this motion. Not down, for this motion. There what happened was, normally here t time, this is velocity. At the beginning, the velocity of the sphere was 0, start from here. But we know that gradient of velocity time graph is acceleration. Gradient is the inclination, this one. So acceleration reduces, that means this inclination should reduce. And it should come to 0 also. No. Therefore, the graph is like this. Acceleration reduces. And it comes to horizontal line. We'll say this is the time is t there. This is the terminal velocity. Terminal velocity, or that is Vmax. Until that, this gradient reduces. This is the particular time the sphere attains terminal velocity. You better write terminal velocity just like a TV then. So then this is the graph. If there is no need to draw this, what I'm drawing in blue, this acceleration considered here. See, this angle reduces. That means acceleration reduces. Don't draw that blue one, but if you want, when they ask you to draw, only draw the curve. Remember, this is correct for when there is a steady flow, steady motion of the sphere. If steady motion situation breaks when the sphere is falling down very fast. That means higher velocities. Right. Now I will consider another situation where the sphere is moving vertically upwards. So this is a liquid, inside you keep it. At the beginning you get its weight vertically down, not down, heading. When the sphere is moving vertically upwards in a fluid. Fluid means in a gas or liquid. Then upthrust is acting on this. When it is completely in the liquid or water or whatever it is, center of buoyancy and center of gravity of the sphere both are at the same place, acting at the same place. And the other situation, this is moving upwards with velocity of v later. Now the frictional force downwards. Why? Against the motion. Frictional force means viscous force. Now resultant force is, you better draw this one. Okay, now can see, no? Now the resultant force R is equal to upwards. Now I'm talking about upwards resultant U minus mg minus f. This can be written as U minus mg plus f. That is R. Then what happened is, there is a resultant force upwards. Therefore, there is an acceleration upwards. Acceleration increases, velocity increases, and according Fy is directly proportional to V. Therefore, F increases. Then mg plus F value. Mg is a constant, F increases. Then U minus mg plus F value. This increases, difference decreases. That means resultant force decreases. Still there is an acceleration, but acceleration reduces. In this way, it goes on, and there is a situation U is equal to mg plus F. Then resultant force becomes 0. After that, no further acceleration. Then that situation, the sphere is getting the maximum velocity. After that, no any increase of the velocity. So this situation is concerned resultant zero, velocity becomes maximum, or acceleration is zero, then velocity becomes maximum. That is called terminal velocity. Normally we say the sphere has attained the terminal velocity. Right. I'll give the note now. Consider the situation, a sphere is kept inside, a fluid, especially a liquid. When the sphere is released, at the first situation, on the sphere, following forces are acting. Number one, upthrust, vertically upwards. Number two, its weight, vertically downwards. Weight of the sphere, vertically downwards. Number three, when it is moving upwards, viscous force, vertically downwards. Within brackets, you write against the motion. Now, there is a resultant force. It is equal to, then write this step. R is equal to U minus mg minus F. R is equal to U minus, within brackets, mg plus F. Right after this. Then write, since there is a resultant force upwards, there is an acceleration upwards. Then the velocity of the sphere increases. According to Stokes Law, F is directly proportional to velocity. Therefore, viscous force increases. Then it is obvious that the value of mg plus F increases. Again, consider R equals U minus mg plus F. The difference U minus mg plus F decreases. Therefore, the resultant force decreases. But since there is a resultant force, still there is an acceleration vertically upwards. That acceleration is less than the earlier. That means still velocity of the sphere increases. That means still velocity of the sphere increases. In this situation, there is a particular situation, u is equal to mg plus f. Then there is a particular situation, u is equal to mg plus f. U is equal to mg plus f. Then the resultant becomes 0. Or resultant force becomes 0. Then there is no acceleration. A becomes 0. After this situation, velocity of the sphere does not increase. In other words, when the acceleration becomes 0, the velocity of the sphere reaches the maximum velocity. The velocity of the sphere reaches to maximum velocity. This maximum velocity is called terminal velocity. Just draw this and note down up to this. After that, write definition of terminal velocity. When a sphere is moving vertically up or down in a fluid, there is a situation where the acceleration of the sphere comes to 0. Comma. At this instant, the maximum velocity is there for the sphere, and this maximum velocity is called terminal velocity. Even the object is, the sphere is moving upwards. When you plot a graph, VT graph, velocity time graph, the velocity time graph shape is the same as the early. So then you draw the same one like that, and this is parallel after this. This is the particular time where it reaches its terminal velocity. And this is terminal velocity. velocity of Vmax. This is velocity. Same. Acceleration reduces. But I want to explain further. In some questions, we'll consider about air bubble is coming vertically up from a certain tank or certain river or whatever. Normally, here remember, the liquid must be always in stationary position at rest, not flowing once. In a river, though I said it, it cannot be. River is not flowing. Flowing, then it is correct. But river is concerned, it's flowing liquid. In a tank, that is okay. Because the liquid is or the water is not flowing. Now, sphere is or the air bubble. This is air bubble. Air bubble. Then, normally mg downwards, upthrust is there. Upthrust is there, mg is downwards and viscous force is down. Now, normally, I explained it early, resultant force upwards is U minus, then resultant force R is equal to U minus mg minus F. But there are some situations in question they say ignore the mass. Then m becomes 0. Then R is only equal to U minus F. That situation, terminal velocity is there when upthrust is equal to F. Not down. When an air bubble moves upwards or any other situation, if the question says ignore the mass, then m becomes 0 and then mg becomes 0. Draw it, write like that, then write these two states. Sometimes they say about this situation, in MCQs they say, here this situation, or they describe the situation, after that say upthrust is equal to viscous force, it attains terminal velocity. That is correct. Because mg is not there, that is the situation. Next one. Now I will consider a different situation. Earlier also I said there is another equation And it is not standard equation. You have to prove and get this equation and substitute. Heading. Consider a solid sphere, radius A, comma, density rho, comma, falls vertically down in a liquid steadily and coefficient of viscosity of the liquid is eta. And the density of the liquid is sigma. And the sphere reaches and the sphere attains terminal velocity of v. Terminal velocity of v. Considering gravitational acceleration as g, considering gravitational acceleration as g, prove an equation for the terminal velocity. Prove an equation for the terminal velocity. Actually, the situation is concerned radius A, density rho, it's falling down, terminal velocity V, eta is the liquid coefficient of viscosity and sigma is the density. Fluid. All will say liquid. This is coefficient of viscosity. This is the situation which I said. Just draw this picture. Because when you draw these pictures and keep in your book, you get the idea at once before reading the notes. When you're reading before the exam or in future. Now we'll consider the situation. Here the sphere radius is A, then downwards you get mg, mass is m, weight is mg. That's falling downwards. Upthrust is acting there, u, and terminal velocity, v, and this density is rho. Same thing, you should not draw again. You are drawn, if you want, you draw it. Eta and sigma density. Now I want to get in two values first. Mass. I want to get a mass, but you can write directly. But I'll explain it, but you can write the mass of the sphere. M is equal to volume of the sphere into density of the sphere. Actually, this is not to be shown, but you note it down at the exam. This is not there. If you want, you write it. It won't be a problem. So M is equal to sphere volume 4 by 3 pi a cube, a to the power 3, into density. Density is rho. So without this multiplication sign, I'll write directly. That is same. You can write at once, but if you want, write like that. Then upthrust is equal to weight of the liquid. So first I write volume. Volume of liquid displaced. That is equal to volume of the sphere. 3/4 pi a to the power q. Then mass of the liquid displaced. Volume into V into rho. So that means 4 by 3 pi a cube into rho. This is density. That means sigma. Then upthrust is equal to U is equal to 4 by 3 pi a to the power 3 sigma g. Because weight of the, if you want, you write here weight. Weight of the liquid displaced into G. Therefore, upthrust is equal to 4 by 3 pi a cube sigma G. Here, if you are writing this directly and if you are writing this directly, it is not a matter for this. But for hydrostatics, you have to prove like that. But here there is no need. We can write directly mass is this much and we can directly write upthrust is equal to this. But anyhow, note down up to this point. Again, I'll tell you, you can write this at once. You can write this at once for this equation when you are proving. Right. Now, see what is happening. Now, we can apply F equals M at the terminal velocity. At the terminal velocity, A is equal to 0. So then F equals MA, simple method. Sometimes different statements are given and this is the easiest way, downwards. F is the resultant force. Mg, downwards Mg. Then here the viscous force F is there, upwards. Mg minus U minus F is equal to mass into 0. Why? A is 0. This is 0. Then mg is equal to u plus f. Easy purpose, we'll write it. But f is equal to 6 pi a eta v according to Stokes law. Then mg is equal to u upthrust plus f. Directly we substitute the values. mg, m is equal to 4 by 3 pi a cube rho g is equal to 4 by 3 pi a cube sigma g plus 6 pi a eta v. Then look at this. When you look at all the terms are concerned, there are 3 terms here. Pi is common, I divide it by pi. And here you can divide it by a also. Divide it by pi, divide it by a, divide it by 2. All can be done. When you divide it by a, then this a cancels off, this becomes 2 and this becomes 2. And you can divide it by, as I said, by 2 also. When you divide it by 2, here you get 2, here you get 2, here you get 3. Then the equation becomes 2 by 3 a squared rho g is equal to 2 by 3 a squared sigma g plus 3 eta v. I'll change the 2 directions and write, or I can multiply it by this 3. Then this 3, 2a squared rho g is equal to 2a squared sigma g plus 9 eta v. 3 into 3 is 9. 9 eta v multiplied by 3. Then 9 eta v is equal to 2a squared rho g plus 2a squared sigma g. No, 9 is equal to minus 2a squared. Then this is equal to 2a squared rho minus sigma into g. G is also common, I could have taken here, but I wrote it up there because standard we are writing like this. Now this is 9 eta v. So v is equal to 2a squared rho minus sigma g divided by 9 eta. This is not a standard equation, but you have to prove and get it. Then note it down. Always remember, when you substitute the values, some going up also we can prove, rho minus sigma is substituted, this value must be, difference must be positive. Otherwise you are writing in the wrong way. Again, I'm saying, I'm going to tell you, this is not standard. You have to prove and get it. Finally, in brief, finally you draw this one and you can understand this because this is a mass of the sphere. But anyhow, terminal velocity V is equal to 2a squared rho minus sigma into g over 9 eta. So this one again draw and write it. It is quite enough to see without going through this always the time. Always. But remember, this is a solid sphere. Solid sphere. Rho. Density is greater than liquid density. Liquid value. So therefore, rho minus sigma is greater than 0. That means this is positive. Always you should get when you substitute positive value for this. Otherwise, you have done something wrong for the densities. Note down that also. Now, the sphere is, next one, then write it in. When the sphere is moving upwards, I'm not going to explain like the early, quickly I'll do it. mg downwards, this is moving upwards. V is the terminal velocity. And we know that U is upwards, acting here. And the other one is viscous force downwards. This is U. Directly I'll write this density is rho and this is sigma, liquid one. This is eta, liquid. Then anyhow, directly I am writing m is equal to 4 by 3 pi a cube radius cube rho. Upthrust is U is equal to 4 by 3 pi a cube sigma. Sigma is the density of this into G, weight of the liquid displaced. Now, according to F equals ma, vertically upwards, at the terminal velocity, A is 0. Then F is equal to, F is vertically upwards, U minus F minus mg is equal to mass into 0. What is this? Acceleration. Then you get, after that you get U minus F minus mg is equal to 0. U is equal to, F is equal to, if you want to get to the other side, then we can say directly minus F is equal to mg minus U. F is equal to U minus mg. U minus mg. In this case, remember, when it is moving upwards, sigma must be greater than rho. Then only it goes up. Now, I'm substituting the values. F is equal to, that also we can write here, 6 phi A eta V, V is the terminal velocity. Then F plus is equal to U minus mg, 6 pi A eta B is equal to U. U is equal to upthrust, 4 by 3 pi A cube sigma G minus 4 by 3 pi A cube, then rho G. This is G. Here G is not there, only M. Then as I simplified early, I can really cancel off pi. Then A, 1A, this becomes 2, this becomes 2. Then after that it is divided by 2, divided by A, divided by, then pi divided by 2. Then 3, 2, 2. This is pi separately. Now you get 3 eta V is equal to 2 by 3 A squared sigma G minus 2 by 3 A squared rho G. Then multiplied by 3. 9 eta V is equal to 2A squared sigma G minus 2A squared rho G. Now it is equal to 2A squared sigma minus rho G. 9 eta V. V is equal to 2A squared sigma minus rho into G over 9 eta. Only the difference, early rho minus sigma, this is sigma minus rho. Because sigma is here, the sigma value is greater, rho value is less. That is the reason it goes up. Note it down. Right. Now I'll explain another situation. In some questions, they say, then write, when an air bubble is, when an air bubble is moving up vertically upwards in a fluid, in questions, sometimes it says, ignore the mass. Ignore the mass. Then this is 0, m is 0. Then F equals ma vertically upwards, u minus F is equal to 0. U is equal to F. U is 4 by 3 pi a to the power 3 sigma g is equal to 6 pi a eta v. From this, we can phi cancel off, 1a cancel off, then divided by 2, that is 3, this is 2. Got it now? Then directly V is equal to 2a squared sigma g divided by 9 eta. Like that small equation comes. There are some situations, according to that, you have to perform or do the question. I'll explain how to answer for the questions also. Then write, when a solid sphere or metal sphere is falling down in a viscous liquid, but you have to consider when falling down in a viscous liquid, then normally we are using V equals, what is this equation? V is equal to 2a squared rho minus sigma g over 9 eta. Eta is normally given. Then remember all the other things also given. That means except one unknown. G is known. This is given. And A radius is given. Rho sigma given. Normally rho value is greater than sigma because this is metal. This is liquid. Then directly you apply and get the answer. No need to then note down this question. radius of a steel sphere, sometimes it is called ball, sphere is 3 millimeters and it falls in a certain oil whose coefficient of viscosity is 2.5 ns m minus 2 and density of 800 kilograms per cubic meter. Density of steel is 8,000. Density of steel is 8,000 kilograms per cubic meter. Find the terminal velocity. Find the terminal velocity of the sphere. Sketch, second part, sketch velocity time graph and show the terminal velocity there. Then what you have to do is, you have to draw the normal sketching means like this. Here, the value what you are getting for value should be marked here. Not terminal velocity, labeling, but here sketching is concerned, velocity time should be marked. And it should be horizontal from there. Time is not asked by me. So this is the velocity. Don't write Vmax or V terminal. There you draw the value. Write the value there. Then you get the equation. Now I'll come to another one. Then this situation, sometimes the questions are based on a different way. Some kind of grains are scattered on the surface of water or any liquid, and then it goes down. But grains, sand, all are concerned, there are some different situations. Then right, in some questions, it says sand particles sand particles are scattered on the free surface of water, within brackets liquid. Or some questions, it is some grain are scattered on the free surface. On the free surface. There are situations like that. But remember what I say, why I said it. Here, grains or sand is concerned, those are not spheres, no? So we have to write assumptions. Number one, assumptions. Then, sand particles are considered as small spheres. Spheres, note down. I will give another clue, but I'll explain after this. Then sand particles attains terminal velocity from the free surface. That means there is no need to fall downwards and we consider it falls, it gets the terminal velocity from this point. I'll explain that. Right? These two are to be considered always. But if the question says those are spheres considered, don't write as this one, then you write only this assumption. If they say those are spheres. Understood? Now, those two here. Even, then write, even for the grains, these two can be written. I will tell another special thing now. Normally, practically, then write, practically, when a sphere falls, 6 times of its diameter. 6 times of its diameter. The sphere attains terminal velocity. So sand particles are, sand particles are grains, are having small diameters, just like the two diameter, two. We assume it attains terminal velocity from the start, within brackets, from the free surface. There is another thing I have to explain. Now, sand or grains or sand particles are concerned, they are not having the same size. Then the sand particles of grains are concerned, they are not having the same size. If we consider them as spheres, the radii of sand particles and grains vary. That vary. Now look at one of these, it's enough. We'll consider different size particles. The equation related to this is V is equal to 2a squared rho minus sigma g over 9 eta. So all these are constant for a given situation. Eta, rho, sigma, g, 2 all are same. So terminal velocity directly proportional to square of the radius. Right. Then write. First draw like that and then write this equation, then come up to this. Here then write according to this, terminal velocity directly proportional to square of the radius. Square of the radius. Therefore, the largest particle gets the largest terminal velocity. Largest A. The particle which has the smallest radius gets the lowest terminal velocity. Largest one is having large velocity, large terminal velocity. Therefore, if you consider this as the height is capital H, terminal velocity V, then time is equal to distance divided by velocity. Then T equals H over V. We can calculate the time reached. But T is, this is a constant, inversely proportional to V. Then largest terminal velocity is having a certain particle, the T is smallest. That means the largest particle is getting largest terminal velocity and it reaches the bottom first because T is smaller. Then right? If we consider if we consider time taken to reach the bottom of the container by any particle, then largest terminal velocity particle is concerned, it reaches first to the bottom. Since time taken is inversely proportional to terminal velocity. Then right? Since time taken is inversely proportional to terminal velocity. Highest terminal velocity, then right? When the terminal velocity is having the highest value, the time is the least. Time is the least. Then we can say next one. The particle with the smallest radius gets the smallest terminal velocity and the time taken to reach the bottom is having the largest value. In other words, the smallest particle reaches the bottom finally. Or we can say the particle with the smallest radius settles down at the bottom finally. Now you understood what is happening, no? The largest one reaches the bottom quickly Normally, when we scatter this in a liquid surface, what happens is various sizes are there. So therefore, one is having the largest one reaches the bottom first. But largest one comes to the bottom with the largest time factor or time taken is largest. But if you give any time in between, the largest one reaches there in T1, smallest one reaches, this is the largest, T2. If you consider any particular time between T1 and T2 as T dash, then what has happened? Certain one with a higher, lower radius has reached that. But others are still in the liquid. Now we normally call them, or we say the some other particles are still in suspension with the liquid. Then right? If we consider the largest particle takes time T1 to reach the bottom and smallest particle takes T2, time T2 to reach as the bottom. Then T2 is greater than T1. T2 is greater than T1. If we consider any particular time between T1 and T2 as T dash, some particles has settled at the bottom, and some particles which are having less radii are still in the liquid, or in other words, they are in suspension. In the liquid. If they say, we'll say after 5 minutes or after 40 seconds, then 40 seconds, some particle is there. More than that, all are at the bottom, but just below the value of this radii is very close to the bottom because it is having a greater. Then we can, in question, they can ask after a particular time, what is the largest radii of the particle which is still in suspension? Then what you do is, then right, in some question they ask, find the largest radius of the particle in suspension in the liquid after particular time, we'll say T dash. T dash. The time is given, but T dash is between T2 and T1. This is there. Then we can calculate T dash. T is equal to h over height over terminal velocity, V terminal. Then T dash is equal to h over V terminal. So V terminal is equal to h over T dash. H is given, T dash is given. Then we can find terminal velocity. Then write, when the particular time is given, we can find the terminal velocity related to that. Then we can find the radius of the particle which settles at that time at the bottom. Radius of the particle which settles at the bottom at that time. So then V is equal to 2a squared rho minus sigma g over 9 eta. When you consider this is terminal velocity, this is found. This is known. Sigma rho. All are known now. Sorry, A is not known. G is known, eta is known. We can find A. But it is at the bottom, no? But bottom is concerned that time largest particle. This is the radius of the largest particle. But it is near the bottom. Then if such a question is given, what you do is, time is concerned, find the terminal velocity. After that, you substitute here. Then you can find A. It reaches there because other smaller ones are still there. The largest particle, diameter, or we can find radius here. If they ask diameter, multiply by 2 and give the answer. Right. Now I'll quickly finish the other things. Now look at this. Another situation. Normally, not when raindrop falls, it starts its journey from very high altitudes. It starts its journey from very high altitude. Altitudes mean very high, larger heights. If you consider the height is 2 kilometers or 1 kilometer or 2 kilometers, the cloud is at, rain cloud is at 2 kilometers. Then when it reaches the earth, V squared is equal to U squared plus 2AS. V squared is equal to 0 squared plus 2 into A is G, 10 into S, 2000 meters. So V squared is equal to then 4, 1, 2, 3, 4. So V is equal to square root of 4,000. That means V is equal to 200 ms minus 1. So if the raindrops comes like that and hit us when you are going or even we are holding an umbrella, it will really, the raindrop can pierce the cloth of the umbrella. Or if it falls on our body, it will hurt us. Because the momentum is concerned, it is larger. Very large value. Then it won't be happening like this. What happened is, from the cloud it comes down. Then viscosity is there. mg downwards. Upthrust is there, U. then the raindrop reaches or attains the terminal velocity. Then right, when the raindrop just falls and consider its velocity when it reaches the earth, it's a very large value. But it won't be happening when the raindrop falls in the air. It attains terminal velocity quickly and then fall with that. Then fall with that velocity. It can be calculated using the equation 2a squared rho minus sigma g over 9 eta. Eta for air. So this is water. Sigma is other density, air. A is radius of the raindrop. Then you can consider the terminal velocity, and that is the velocity it comes down to the earth. Note down this. Two identical raindrops are falling with the terminal velocity of 2 ms minus 1. And they combine together in the air. Find the new terminal velocity of composite raindrop. That means combined raindrop. We'll consider like this. This is radius is A1 and terminal velocity is V1 initially. There are two drops, A1, V1. For one is, it is 1, we can write V1 is equal to 2A1 squared rho minus sigma into G over 9 eta. Now they combine together. Then you get a large one. This is A2. This was actually A1 plus another A1. Okay. So then V1 volume V1, oh, we'll say simple V1, volume V2. So volume of these two are added, volume of this is equal. So volume of A1 is 4 by 3 pi A1 cube, volume of 1, plus 4 by 3 pi A1 cube. If they say two different values, two drops are having two different values, second one, another one, is equal to 4 by 3 pi A2 cube. That is the new one radius. 3 here, cancel off. Then A2 cube is equal to A1 cube plus A1 cube. That means 2A1 cube is equal to A2 cube. Understood? Then A2 is equal to 2A1 cube, 1/3, third square. Then this is equal to A2 is equal to A2 is equal to 2 to the power 1 over 3 A1, because this is 3 into 1, 3. That's so like that we can get. Understood, no? After that, you apply again V is equal to 2A2 square rho minus sigma G over 9 eta. This is the first equation. This is the second equation. Then if you divide, this is V2. Second one divided by the first one. Then V2 over V1 is equal to 2A2 squared rho minus sigma G divided by 9 eta divided by 2A1 squared rho minus sigma G 9 eta. See what's happening? All those are getting cancelled. Then V2 over V1 is equal to A2 squared over A1 squared. A2 value can be taken from here and substitute. V2 over V1 is equal to A2 squared. That means 2 1/3 A1 to the power 2 divided by A1 squared. Then this can be simplified. V2 over V1, 2 to the power 2 by 3. Powers are 2. Then A1 squared over A1 squared. So these two cancel off. Then V2 is equal to 2 to the power 2 by 3 V1. V1 is given as 2. Then you can get the answer. Any drops are connected, 2 or 3 like that. Total volume of the initial added to get total volume, that is the addition of all the volumes of all drops or spheres, are equal to the final one. Volume or volume of the final one. Quickly write, note down. Now I'll tell you certain things related to viscous liquids. Then write. Temperature increases, coefficient of viscosity decreases. Coefficient of viscosity decreases. So then temperature increases, coefficient of viscosity decreases. So with the time it decreases. If you consider temperature here and coefficient of viscosity here, then it reduces like this. It reduces. It doesn't come to zero, remember. No temperature that it becomes zero. Just sketch it. Coefficient of viscosity here. Day-to-day life, we are using this. Normally, especially in making sweets, in Sri Lanka, so traditional Sinhalese people and Tamil people and even Muslim, everybody, all are concerned, they are having traditional foods. When they are making something like that, we'll say it is calm or any kind of thing, you have to mix treacle with this flour or any other particles. But if we are not doing it directly, we heat it up, then the viscosity is becoming less. Then what happens is the particle, in between the particle, this liquid treacle can go easily. Even not like that, even in Sri Lanka still we are using this tarring. Tarring means putting tar. Now most of the time carpet is there, and that is a different one, liquid. That is a concerned tar. Early came as solid, semi-solid one. But we have to increase the temperature of that 10, then it will become liquid, and further we increase the temperature of that, then the viscosity, coefficient of viscosity reduces. Then on the road, then small stones are there, those are normally called metals. In between, nicely the tar goes. Or so then, right? The right examples. Before putting tar to the road, it is being heated to higher temperature. Then coefficient of tar reduces and tar goes into the space between small stones, which is called metals. Second one, when sweets are made, flowers or some crushed grains are to be mixed with treacle. Always the treacle is heated to higher temperature and mix. Then the viscosity, coefficient of viscosity of treacle reduces and mix, means the treacle goes in between the food particles. There are some situations like that. Other than that, I want to explain another thing. That is, normally most of the countries, or even Sri Lanka, also concerned, high blood pressure is normally with the age. That means people say blood pressure, but it is high blood pressure. When we consider about high blood pressure, it occurs according to various situations. One is the heart can't pump it clearly. Right? So then the one is narrowed tubes. Right? In the body, blood is supplied through the large ones and finally capillaries. This diameter is becoming smaller after mostly depositing the calcium or mainly cholesterol. Then what happened? Diameter reduces. Then it can't go properly. So therefore, we have to increase the pressure to send it. Therefore, the drugs are concerned, this flowing, if you consider about Poisson's equation, according to that, Q is equal to pi a to the power 4, then pressure difference P minus P1 minus P2 1 minus P2 divided by 8 eta L. Now length is the same, diameter reduces, then rate reduces. Diameter reduces because of the cholesterol deposit or calcium deposit. Then Q is less. Q is less, the enough volume of blood is not supplied to the cells. So we have to maintain this. So therefore, one situation we can say, we can increase A. Increase A means this must be expanded, the capillaries and all. For that, different drug is there. Different drug or medicine. One medicine. It expands the diameter. The other method is, if you lower this, lower eta, reduce eta, then again Q increases. So therefore, some drugs are given to decrease eta. Right? That is another pressure drug. There are some other drugs to stop angina, heart attacks, strokes, those things. I'm not talking about that. There are another 2 or 3. But basically, a person is given 2 drugs like that. Sometimes the 2 drugs are combined together and one kind of tablet is there. Those are combination. But if you take these drugs, your blood pressure reduces to normal. After certain days, that is normal. Then you can't stop it. It happened because of these 2 drugs. If you stop taking these 2 drugs, what happens again? Expansion reduces, then eta increases. Eta increases, Q decreases, expand, this reduces, eta decreases. Then what happens? Here, eta increases, this reduces. Again, the blood pressure comes because this quantity should be supplied. Then heart should pump with a higher rate. Then the blood pressure goes up. So then a patient, when you get blood pressure due to these reasons, should continue these drugs until the person dies. So then viscosity is a major thing in that. Remember, some drugs are given in order to do like that. But past papers and all the other questions will be discussed next week. Today's lesson is over. Thank you.